now we're going to look at half-life in terms of radioactive decay. And before we do that, we're going to understand what we mean by radioactive decay of a sample of radioactive material. So far we've looked at nuclear decay. We've looked at what happens when a nucleus decays radioactively in order to become more stable. And we know that some nuclei will decay by alpha, losing protons and neutrons. And we know that some nuclei will decay by beta, losing a neutron and turning into a proton and an electron, the electron being ejected from the nucleus. So that's what we've done so far. Now I want us to turn our attention to a piece of radioactive material. So we've got a chunk of radioactive material here, let's call it uranium, and it's full of uranium nuclei. And what those uranium nuclei will do is randomly and spontaneously they will decay. Let's squeeze a few more in here at the bottom. So there's our chunk of uranium. And that uranium nuclei during a certain time period, it might be minutes, it might be hours, it might be years, it might be seconds, it might be milliseconds, will certain uranium nuclei, so these are all uranium, will decay, and we'll do uranium decaying by alpha to give us thorium. So here are all our uranium nuclei. What's going to happen is every now and again one of these uranium nuclei will decay, giving out an alpha particle, and will change to thorium. Might be 1, might be 2, might be 3, depending on the decay rate, how quickly that material decays. And so a bit later on you might get another release of an alpha particle and another thorium, and again another one. And remember, because it's random, we don't know which nucleus is going to decay when. But you can see that eventually, after a certain period of time, all those uranium nuclei will have decayed into thorium. Make sense? So within a piece of radioactive material, those nuclei will decay, and they will decay and produce another element according to the decay. And we've looked at the equations to calculate or to balance those equations in terms of decay and see which elements are produced. Remember that you won't be expected to remember the periodic table and what the mass number and atomic number of elements are, but you will be expected to put in the mass number and the atomic number caused from an alpha or a beta decay. So you won't need to know what the exact element is, but you will have to identify what the mass and atomic numbers are. So back to where we were. We've got a nucleus. We know it can decay by alpha or beta, and of course gamma. We're concentrating on alpha and beta here. We're now going to translate it to a chunk of radioactive material, and we've seen that this piece of uranium that's going to decay by alpha, over time we will lose all those uranium nuclei and they will all become thorium nuclei. So eventually that piece of material will all be thorium. And different materials decay at different rates, so different numbers of alpha particles might be released in the same time period for different materials. So some might decay very quickly, losing a lot of activity in milliseconds, whereas other materials will decay very, very slowly, and it will take hundreds of thousands of years for that decay to fall. But you can imagine what's going to happen in that eventually your chunk of your full uranium is going to become a chunk of thorium. The thorium, of course, might go on to decay itself, but for now let's just concentrate on what happens to this chunk of uranium. So this piece of uranium is going to become a piece of thorium with all its nuclei in there. And we need a way of describing mathematically how quickly that happens, and we use the term half-life that we've got up here. And the definition of half-life is important. It comes up over and over and over again in exam questions, and it is the time taken for the number of nuclei in a radioactive sample to decay by half. To decay by half. The half-life. So what are the important bits? It is a time, and most important of all, it is the number of nuclei, not the number of atoms. That's where most people fall out. They will put the time for the number of atoms to fall by half, or the time for half the atoms. None of those will get marks because you need to say nuclei. It's only about the nuclei. They are really picky about that. You can also use activity, so you can get rid of number of nuclei and substitute that with activity. So it can be the time taken for the activity of a sample to fall by half. So instead of nuclei, we can have activity here. And it's the same thing. If you think about, you've got a sample of 1,000 nuclei and every 2 seconds 0.1 of them decay. If you halve that sample and still 0.1 of them decay every so many seconds, you are going to have half the number of decays. And remember, it's the decays that give you the activity. So it doesn't matter whether it's activity or number of nuclei. They work out mathematically as the same thing in this instance. So what are they going to ask you to do with that? They're going to ask you firstly to define it, and you cannot forget that definition. You must learn it because it is very, very common. I'd say 80% of papers I've seen that definition being asked for. And also very common questions are calculations of half-lives. So the other common questions are about calculations of half-life. And a way to get into calculations of half-life are to imagine what happens in terms of nuclei. So I'm going to take, for example, 1,000 nuclei. I'm going to say I've got a sample with 1,000 nuclei in it. And after one half-life, I am going to end up with 500 nuclei. After another half-life, because it's the time it takes for halving it, I'm going to end up with 250 nuclei. After another half-life, I'm going to end up with 125 nuclei. Does that make sense? So the half-life is the time it takes for the number of nuclei to fall by half. So in this instance, we might have a half-life of 2 seconds here. So 2 seconds, we've gone from 1,000 to 500. In another 2 seconds, we've gone from 500 to 250. And in another 2 seconds, we've gone from 250 to 125 nuclei. So what are the sort of questions around those calculations? Let's have a look at what they might ask you. So for example, the first one might be what we just did now. So if we start with, they give you the initial number of nuclei. So they give you 1,000. They might give you the half-life. They might say the half-life is 2 seconds. And they might ask you, how long does it take to get to, for example, 125 nuclei? So how long does it take to get to a certain number of nuclei? So they give you the initial number, they give you the half-life, and they might say, how long does it take, for example, to get to 250 nuclei? What would you do there? So you'd start off with your 1,000, you'd draw your little loop, take it to 500, you know that that's taken 2 seconds. Draw your little loop again from 500 to 250, you know that's taken 2 seconds. You're now at 250, so you know that's the number of nuclei they wanted. How long did it take? 2 seconds here and 2 seconds here, so the total time is 4 seconds. So the question is, we started with 1,000 nuclei. If there's a half-life of 2 seconds, how long did it take for the sample to decay to 250 nuclei, or an activity of 250 becquerels? And remember, you halve it. Keep halving it until you get to the number of nuclei that they've asked you for or they've given you, and then work out how long that took. So they could, for example, ask you how long it took to get to 125 nuclei. So again, you would start off with 1,000, do your loop 500, second loop 250, second loop 125. You know, each of those took 2 seconds. So you know your total time to get to 125 nuclei would be 6 seconds. Remember, that can be in hours, minutes, years, or whatever. Another way you can use this kind of looping idea between half-lives is if they give you a different question and they ask you, what is the half-life? So they might say, it took so long to get to X number of nuclei. What is the half-life? So let's start and demonstrate this again. So they might say, give you the initial number, they give you 1,000, and they're now going to say, after 12 hours, so after 12 hours, we got to 125 nuclei. What is the half-life? So they give you the time, they give you the initial number, they give you the final number, and they want you to calculate the half-life. So you've got to find the half-life from that. So let's do it with our looping method. So we start off with 1,000. We know that after 1 half-life we're going to have 500. We know that after 2 half-lives we're going to have 250. And after 3 half-lives we're going to have 125. We know that that whole period took 12 hours. And we know that in that period we've got 1, 2, 3 half-lives. 1, 2, 3. So what's the period time for 1 half-life? It's 12 divided by 3, which is 4. So the half-life here is 4 hours. Both of those methods, both of those sorts of questions, either asking you how many nuclei are left after a certain amount of time, or asking you what the half-life is, or they can ask you how long did it take. If the half-life was 4 hours, how long did it take to get to 125? Then you would do 1, 2, 3, and you do 3 times what that half-life. So what are the number of nuclei at the end? How long did it take to get to a certain number of nuclei, and calculating the half-life can all be done using this model where you start off with the number of nuclei they've given you and you keep halving it and writing the numbers down until you get to the number that they want at the end, or you've done the number of half-life loops that they might ask for. So that's a way of calculating it, and I'm going to go on to a little bit more difficult way of calculating it, but not a more difficult, a more mathematical way of calculating it. So if you need to understand, and that I would say is one of the most common methods used that I see on exam papers year on year, is that kind of looping model of way to do it. But if you're more mathematically inclined, you can look at it a bit more like this. So let's have a look at what happens. Here's our initial number of nuclei. Okay, they're all uranium. After 1 half-life, we've got half of them uranium. After 2 half-lives, we've got 2/3 of them thorium, so we've only got 1/4 left. After 3 half-lives, we've got only 1/8 left. So let's colour in our uranium. So here we have all uranium. Now we've only got half uranium. Now we've only got 1/4 uranium. Now we've only got 1/8 uranium. That makes sense, doesn't it? So we've halved it once, twice, 3 times to get 1/8. And that makes sense because that's what we did in the last looping model. So how does this work? We know that we've got 1, we go to 1/2, we go to 1/4, and we go to 1/8. And we know that this is 1 half-life, this is 2 half-lives, this is 3 half-lives. And we can simplify that to save you doing this sort of looping idea if that if it's the mass and if it's equations that really rock your boat, then we can do it like this. So what we do is we say the number of nuclei or the activity at the end. I'm going to use n just to make it clear, but it will be the same as A. The number of activity left at the end are the number of nuclei at the start times a half after 1 half-life, a quarter after 2 half-lives, an eighth after 3 half-lives. Now, to save you having to work out whether it's a quarter, a half or an eighth, you can write it like this. You can say n naught times 1 over 2 to the power n, where n is the number of half-lives. So 1 over 2 to the power n, where n is the number of half-lives. And let's just see if that works. Does that make sense? So let's have a look. After 2 half-lives, we're expecting to have a quarter. That's right, 2 to the power 2 is 4. So it's 1 over a quarter, which is exactly right. After 3 half-lives, we've got 2 to the power 3. 2 to the power 3 is 2 times 2 times 2, which is 8. So it's 1/8. So you can see that it fits in with our model up here of how that half-life affects the number of nuclei. So if you're mathsy and you don't want to do that looping model, remember that equation, and remember this can be A or N. So activity equals the initial activity multiplied by 1 over 2 to the power n, where n is the number of half-lives. And remember, you've still got to work out the number of half-lives. So if we think about our calculation a bit earlier on, where we looked at, we wanted to know the number of nuclei remaining in 12 hours if the half-life was 4 hours. How would we use this equation to do that? Well, we want to know, we started off with 1,000 nuclei. Yeah. We know that we had 12 hours and we had the half-life as 4 hours. So we know that the number of half-lives, if we've got 12 hours and the half-life is 4 hours, we know that we've had 3 half-lives. 4, 0 to 4, 4 to 8, 8 to 12. So we've gone 1 to the power 3. Sorry, 2 to the power 3. 2 to the power 3 is an eighth. 1,000 times an eighth is 125. So it's another way of getting the same answer to the calculation, the question before, how many nuclei are left after 12 hours. So 2 ways of doing those calculations. They're quite tricky, and it might mean you need to go back over this video and kind of do it slowly, but both ways are equally valid. If you are the sort of person who likes to see how things are built up, then I would use the initial model where you loop and halve the number of half-life each time you do a loop across the top. If you're mathsy and you're happy with the maths, then use the maths. And if you really don't understand much about it, I would say go back over the video again, ask for some help. But the important thing is, if you're really just, at the last minute trying to revise things, learn that equation. Make sure that you, however, can work out what n is. And n is not the time, it's the number of half-lives. Hopefully that makes sense in terms of calculations. There's one other way of you being able to calculate half-life, and that's from a graph. So I'm going to show you how that works now, and then we're going to finish this half-life session. Wait for this to dry properly. So if we were to plot the number of nuclei or the activity, it doesn't matter which, as we said, they both come out the same. If we were to plot, we've taken our big chunk of uranium and we're going to plot what happens to either the number of nuclei or the activity over time. So we've got a time axis. I'm going to do this in seconds just because it's an SI unit and it's simpler. You might have it in hours, you might have it in days, you might have it in weeks. you might have it in minutes, so it doesn't really matter what the time axis is, but note the time axis. Against either the number of nuclei, so this will be the number of uranium nuclei remaining if it's your uranium decaying to thorium, or it might be your number of nuclei remaining of any material that is decaying. So it's the number of nuclei remaining of the material that is decaying, not the material that it's decaying into. Or, of course, as we said, the activity, it doesn't matter which one it is. Okay, so let's put some numbers on this. 1, 2, 3, 4. Okay. These in the exam are likely to be very, very high numbers, but I just want you to see how it works from here. So we're going to use this graph now to calculate the half-life of this sample. How do we do it? The first thing we do is we take a number that we can easily halve, that is fairly high on the y-axis. We don't want to be messing around down here, it won't be very accurate. So take a number that's fairly high on the y-axis that we can easily halve. So I've taken 6 because I know that half of 6 is 3. What I'm going to do is I'm going to take a line and I'm going to go to the curve and drop it down onto the time axis. Let's say that the value on this time axis is 1 second, just because we're going to work with easy numbers. Then what I want to do is I want to halve that 6 to 3 and do the same thing again. It's like make a recipe for making a cake. And let's pretend that's 1, 2, 3 on my time axis. So remembering the definition of half-life, it was the time it takes for the activity or the number of nuclei to decay by half. We know that at 1 second there was 6 and at 3 seconds there were 3, so the time it took for that to halve was the interim period between 1 and 3, which is 2 seconds. Now don't get confused just because 2's in the middle of those. Yeah, I'll leave that out just to stop you from getting confused. So it's at 1 second it had 6, at 3 seconds it had 3, so it took 2 seconds for that sample to halve between 6 and 3. I'll just run through that again for you. So you've got the graph. This, incidentally, is called an exponential decay graph if you're into shapes of graphs. To work out the half-life, you are going to select a value on the activity or the nuclei axis that is high on the axis. We're not going to try and go from 2 to 1 or from 1 to a half. It's just a bit messy, it's not as accurate. Take a number high on the axis that you can easily halve. Draw a line to the curve, drop it down to the time area. Record that time or note that time. Halve that value, your 6, to give you 3. Do the same thing again, trace it along to the curve and drop it down onto the time axis. Look at the time when there were half the number of nuclei. Now remembering that it is the time taken to get from there to there, you know that it's going to be 3 minus 1, which is 2 seconds. And you might be thinking, some of you, well, how do I know where to start that? How do I know where to put that first number? And the answer to that is it doesn't matter. The nature of the exponential decay curve tells us that wherever you put that number, as long as you halve it, you will get the same time period in between. And I'll give you a little example. If we were to, for example, to take 4 and 2, and we'll see how well drawn my curve is. 4 and 2. Okay, that distance should be the same as that distance. It shouldn't matter whether you use 3 and 6, 4 and 2, 5 and 2.5, whatever you decide to use, as long as you follow the method, okay, you will get the same answer. So these distances should all be the same, and you can see that my curve isn't as perfectly drawn as it should be, because these blocks should all be the same, and in the exam the graph that they will give you will all be the same. So the recipe for this is, number one, take a point high on the y-axis, trace it down to get the corresponding time. Here, that's number two. Number three, halve this value, trace it along to the curve and get the corresponding time, and work out the distance between those two. Hopefully that is clear to you. If there are any questions about that, please drop me an email. If you want me to go over or explain anything a bit more, or do a little bit more work on any of these topics, then drop me an email and I'll put some more information on. But that should hopefully help you with half-life. Where do people go wrong with these? In terms of the calculations, they do not use a model. So they don't either use the looping model or they don't use the calculation model. So they don't really understand. They get the definition wrong because they use atoms instead of nuclei, or particles even instead of nuclei. And they just don't know the method to do the half-life on the graph. I would say the graph one is probably the best done in terms of questions because it's not very difficult. And that really is all they are likely to ask you in terms of half-life. As an aside, if something has a higher activity, if something is decaying more, its curve is going to shift like that. Still going to be the same shape, but it is going to shift further in because we're going to have a quicker drop in the number of nuclei. If the activity is less, then the curve is going to move further out because it's going to take longer for those nuclei to drop. And I think that really is, in a nutshell, most of half-life.